Welcome back, everyone. So I think we are ready to go for another round. Yeah. Great. Thank you very much for having me. Thank you very much for giving me the opportunity to present my research topic. And as every researcher, I love to talk about my research. So please ask any question anytime, and probably we can mingling just after the talk if I got you excited about my topic. But before we jump right into the topic and go into the Hell's Kitchen of research, I would like to introduce myself. This is me for those who are online. I'm researcher and PhD candidate at BTH. Formerly, I was working with Siemens Healthcare, and we're developing software and distributed machine learning algorithm there. Actually a cool topic, but I looked at how software is developed and I thought, okay, this is really how software should be developed? Probably not. And probably I do not disagree with any NDA, but this is why I thought, okay, the problems is not into machine learning, but the problems are in software engineering. That's why I came back to research and try to understand a better way of developing software. Although it's me who's presenting, I have two partners in crime for this research topic. This is Daniel Mendes and Christoph Nook. Just important. I have other partners in crime, but I will just tell along the presentation. I would like to start with a very famous quote. I assume that most, or at least some of you, just know that any organization that designs a system will produce a design whose structure is a copy of the organization's communication structure. So if in this room or in the audience in Zoom, if you're part of an organization that probably designs a system, probably a software system, probably even a complex software system, then you are exactly at this stage. In this talk, we will not focus on the architectural perspective of a system, but on the communication structure. So what is a communication structure then? So a communication within software projects usually consists of multiple layers. So you have different kind of communication media in your teams, in your company. You have Slack, you have email, you have regular meetings, you have workshops, you have code review, you have pull requests, you have bug tracker, what have you, right? Those are stacked on top of each other, and you get a communication structure of the company. The communication, meaning the exchange of information between two people or people, leaves a trace usually, because usually, in particular in computer science or in software engineering, we have a tool which tracks this kind of information. Even meetings are tracked by Outlook or some other tools. In particular, in large and distributed teams, of course, this becomes much more obvious. And it's tool tracked, like we are now on Zoom and we know who's joining this Zoom meeting now. And those tools are exactly our data source. And by the way, if there's one good thing out of Corona, those traces become even more obvious and tangible for us because everyone is now at home and not sitting next to each other. So we understand this is a communication structure. But then, of course, what is then a good communication structure for a good software system in our case? So let's derive this kind of question from stupid examples. So we have here our first communication network. We're not going into the details, but for example, we have here two humans communicating with each other. So there's a type of interaction between those, they exchange information. So we have a tie between those two nodes. We have two teams here, team A and team B. And as you clearly see, the information can be spread, can flow around within these teams in A and B, but not between those teams. There is no connection between those teams. Again, remembering Conway's law, the quote from before, actually this means we have then two separate systems. Systems usually tend to evolve very quickly. So probably this strictly separated thing, having in the same organization, probably contributing to the same product, does not make sense. Probably you want to change that. Probably team A and B are working on separate microservices, but still they're contributing to a product. Let's have a look into another example network. So in this case, almost the same setup, but this red marked circle is now connecting those two networks. So what have we now? Great. So we have a network of two teams which are connected, so the information can be exchanged among those teams. Great. But on the other side, those guy here with the red marked circle is a single point of failure. So if you remove this guy because he retires or he leaves the company, then you still have a separate team, separated teams, not possible of exchanging information. And of course, this guy has a huge workload. So he has two contexts, switching contexts of two teams, exchanging information, syncing them, bringing them together. So the question is then, just can we improve this even more? Okay, in this network, we just have even more connection between those teams. So even if you remove the formerly red dot here in the middle, the network will be stable and the teams can communicate with each other. So the question is then, is the more the better? Yeah, most likely not. The main problem is that, so theoretically, this is the perfect network. So if you come from distributed systems, like cluster computers or even CPUs and their architecture, this is like a fully connected graph, which is the best thing about latency and everything. But the main problem is, well, this is not doable. So for example, in Microsoft, there are over 30,000 developers. You cannot connect everybody with anybody. This is just not possible. And the idea behind, but still, it's a good thing to connect people, bringing people close together. I mean, if this guy in the upper left corner wants to talk to the lower right corner guy, they need that. So in this case, in this case, there are some hops. So how many hops are acceptable? So does this information even get to this guy here? Because it's not directly connected. In this case, it is. Great, but does not scale. So then the question is, where's the sweet spot? Where's the sweet spot of having a lot of connections and making the communication structure as agile as possible, and therefore the product agile as possible, but still being scalable? This is the question. So as a researcher, we would start then to model those complex system. And the model is an abstraction of this reality, which is kind of complex. But we found in our research that existing models are falling short. This means they are not capable of reflecting the communication structures properly. This has many reasons. One is there is no time involved. Do you remember the example graphs we had? This is just, we assume that they have some kind of interaction. But interaction and communication is always time dependent. So information can be invalid over time. Information can be outdated over time. And if not delivered right on time, it might just useless. So the lottery numbers of today are the lottery number of today are super useful yesterday, but have no value today, right? So, and this means it's time dependent. So this node can only exchange information with this node if this happened before that. Otherwise, there is no connection between of them. But even worse, so information is time dependent. This is one thing. The other thing is not every communication is traceable, right? So sometimes you meet someone at a in the cafeteria and you have just a talk. No one is knowing that, but you can get some information from this guy you just met at the coffee machine. And usually communication is not bilateral, meaning it's very rare that only two people are discussing things and exchanging information. Sometimes it's like code. You think of code reviews as a good example for communication, where you exchange information, because usually it's likely that there are two people involved, so like the author and the reviewer, but probably there are more than two people, and existing models do not cover that. And communication in general, but in particular in software engineering, is highly compartmentalized and massive. And just to give you a short idea what this looks like, this is the graph we just had before as an example, constructed the same way with the Microsoft data. This is a huge bulk of, so what can you see there? There's nothing understandable anymore. This is so it's about 30,000 developers, and they are communicating, and it's only 1 month of code review in Microsoft. So this is purely massive. And so what can we get out of that? So visual approaches also for sure. There's a problem. Thanks, we have research. This is our vision. We would like to understand, get a broader understanding of communication, and we would like to make communication networks as a distributed and self-organizing information storage. If you don't like the term information, by the way, you can always replace it by knowledge. Just coming from an academic perspective, knowledge is a very delicate term, so we just stay with information. But in your mind, you can always replace information and knowledge. And those information repositories distribute information without a central instance. So there is no central manager for code review which delegates you are reviewing that guy and stuff like that, or like Slack. You know who to ask. You know who's getting a good feedback for your problem you have. And it's encoding and decoding information on the fly. So there's no thing like, I have to create a wiki page for that. And another very important part is the temporal aspect. Again, I cannot stress it enough. Communication is time dependent, and information is time dependent as well. This means not delivered in time, useless, very old, outdated. And with traditional knowledge repositories or information repositories like wikis, you always have the pain of updating the things, right? But with communication, of course, communication is very often also archived, but the communication itself is not, is always up to date. So if information is distributed, like in every distributed system, then the how, when, and where the information comes from an information source to an information sink is the important part. We need to understand that part. And this means for our research, we would like to focus on the information diffusion. The information diffusion is the spread of information within those networks. So what we have done so far is we developed a solid mathematical model for capturing this kind of complex system, the communication networks. And the communication and the model is capable of handling time, complex and uncertain interactions, communication actions, and of course, the spread of information, the information diffusion. What we do is we use simulations for that. So we simulate spreads in those networks and see how it goes and how it not goes. With those simulations, we try to understand what are the general boundaries of those networks. The networks are empirical, meaning from companies, like those from Microsoft, and but the spread itself is artificial, so to say. But we see the boundaries. How far can we get? But we also have statistical approaches where we try to understand what is then. So this is then the boundary, but what is a reasonable thing, right? So the boundary is not always the ultimate goal. You probably want to have, well, are we good enough to spread and adopt to change in our software system, in communication, or are we not? Like, what is our goal? Although this is, I would say, foundational research and very basic research, I would say there are applications, and I would highlight a few of them. But please feel free to come up with great ideas yourself and just call me, and we make it possible. The first thing is of course, whenever it comes to fundamental research, it's always a problem of understanding. So how is information spread in those networks? Why, where? Those are fundamental things. But with that, there comes a problem. So if Conway's law is correct, then we have a chicken egg problem. So who's going to be first? Is it the system, which prescribes the communication structure, or vice versa? Can we change the system so that the communication structure makes more sense, or is even more capable of handling changes, adaptations to the outside world? Or is it vice versa? Can we change the communication structure and then create better products, more fast, with a faster change pace? The next question is exactly into that direction. Is the change of a system limited to the communication structure and its pace? And of course, the most important one is from a scientific perspective: how, when, and why is information diffused? So so how is the spread going? There is something I would like to introduce you just in a very short note, is the communication pattern. Communication pattern is regularity in those communication patterns. It can be either temporal, like after release, we have a certain increase or decrease of certain types of communication, or it can be topological, like meaning teams which are working together should at least also have a strong connection in communication networks. But with these patterns, the communication becomes predictable, and this is a very fancy thing, because predictable is always a good thing, right? So unpredictable is always kind of it goes into the direction of uncertainty, and this is always not good. But in particular, you can also discuss and exchange best practices of communication, because this is a recurring event, for example, among different companies, meaning, okay, we can discuss pattern A. You know those patterns, like software patterns, architectural patterns, I don't know, the singleton and what have you, right? So all those kind of software patterns, architectural patterns. So you can easily discuss and exchange information. And there's no thing then anymore like, well, I do it the Microsoft way, and we do it the, I don't know, Siemens way, and we do it the like Google way. No, show me what is the pattern and show me what is the benefit of it. Then there's another concept I would like to introduce you as the information smells. We already heard about technical debt. This time it's about information debt. So an information smell is a symptom of an impaired spread of information, meaning the information is not spread immediately or when it's needed, but later. For example, if you have already implemented a feature, and probably someone else has also implemented the same feature already, then this information is too late when the work is already done. So this is very important. And this information diffusion smells, just like technical smells, technical debt. Information smells contributes to information debt, and this can be very costly. Our goal is to have a tool support to indicate those kind of problems. It's not solving the problem, but in the first step, indicating there is a problem because I just have not accessed the data as I need it, when I need it. I have here 3 of the information diffusion smells. One is information overload. So you remember the red circle in the middle, huge workload for a single developer, probably blocking the whole exchange of information through these teams. So you probably need to have a look there. The other one is the bottleneck. The same, the red one was also a bottleneck because it always went through those through this guy. And again, it contradicts to our understanding of communication networks, namely like it's a central node with a lot of power, with a lot of influence, with a lot of with steering management capabilities. I would like to bring up an example from Linux. Yeah, so there's Linus Torvald. In the end, he has this kind of a role, right? So he's sitting at the decide what's going to be happening, not. I probably would say a company does not want to have a guy like Linus Torvald in the end, because this is a very powerful thing, and probably this is not how it should be. And there are memory disorders. When you think about the temporal aspect of information, sometimes you need to like remember information, but sometimes not. Sometimes they are just so. When this meeting starts today, this workshop is not relevant tomorrow, so you can just forget. You can delete this information. If you, but on the other side, sometimes, for example, what an information diffusion smell is, you should keep that to your I don't know, next to their wife's name, because it's super important. Just kidding, but like there are very important information that should not be forgotten. And this is exactly the problem in a memory disorder. This is just switched. You forget things you shouldn't forget, and vice versa. And there's another thing. I'm not sure if your company's working abroad or like outside of Sweden, or operating, having teams there. But if communication networks are distributed and self-managing information repositories, then they also contain non-trivial information. And whenever there's a non-trivial information, the IP comes into play. And the main problem about IP is when it leaves the boundaries of a boundaries of a country. To be very precise about leaving a jurisdiction, then it's taxable. So tax come into play. And whenever tax comes into play, this will be awful. But it's very important. If you're interested into that, transfer pricing is the Google or the Wikipedia page for that kind of stuff. So I'm almost done, but I want to like what we have learned today, or what I try to convince you about. There are 4 different things. The first thing is we would like to understand that communication networks are actually information repositories. Information is stored there. It's encoded, so it's not like easily accessible, but it can be decoded. And they are distributed, so there's no single entity who holds all information. It's distributed, and it's not immediately accessible. You know, like you have to encode this kind of information. I decode in this information, and it's self-organizing. There is no central role there. And then the next big thing is the information diffusion, right next to the name of your wife. Is the spread of information within those communication networks. We found out that existing models are not capable of rendering this kind of complex phenomenons. If you're interested in that, we have a thick paper with a lot of math on within that. We did a simulation with Microsoft with that, and could show that this is just not the existing models do not cover the communication, but this is for the hardcore geeks. And the last but not least, our model makes communication and of course its limitations and problems tangible, measurable, steerable, and predictable. And of course, like the others, I would like to have a call for participation. What we can do in your university, and probably do a good job there, is making some great models, discuss every bit and piece there, and make it sound, prove a lot of things. But what we do not have at university is data. This comes from the company, from the companies. In this case, so far we can rely on those data and a lot of open source projects. But of course, open source is not the same as closed source development. So we are interested into the comparison between those two things. So if you're interested and you have some data you would like to share with us, and to gain some insights about what are the limitations, what are the boundaries of our communication? Can we measure it? Can we make it tangible for transfer pricing, for example? Can we predict future behavior from the existing data? Then give me a call. This is me. I have a Twitter handle. I will also I told you about the huge math paper. It's a preprint. I will share it probably tomorrow or on Friday on Twitter. And if you're really interested, and please check out my GitHub account. There's the simulation code also. So it takes some time. So running the full simulation takes about, depending on your hardware, but so between 24 and 30 hours, because it's such a huge network. But if you're just interested, please have a look. Other than that, then thank you very much again. And if there are any questions, please just be via email or Twitter or now. Thank you.